So we were talking about like we'll have the last session for the revision session, and today we'll cover I'll cover the max Q thing and Form DP in brief, and he'll elaborate this Form DP session, and we'll cover the whole syllabus till tomorrow, and then the next week will be the revision session. Is it fine? And so if you are having any doubts, please post in the Slack so we can take that doubts in the last session as well. Or if you want that some topic should be like discussed in more detail, then we can discuss we can emphasize on that topic. Should we proceed? Okay. Yes.
Okay, madam, proceed.
Okay. So I think you have covered the semi-MDP and SMDP, these things are covered. Max Q only I have to start. Am I correct?
Maybe you can give a little overview of SMTP also, sir, before moving to Max Q.
Or if I'll do the Max Q, in between I'll give the overview of SMDP also.
Yeah, because I could not understand how SMDP is related to hierarchical RL, where it comes into picture, where it is used. So as I understand, hierarchical RL consists of three types. So one is options. The second one is HAM, hierarchical abstraction machines. Third one is Max Q. Where does the SMDP come into picture? Okay, how it is related to that? Maybe you can explain.
Can someone tell him, Yes, come on. I think last session everyone has attended.
Yeah, I mean, we can break down the subtasks, and the subtask taking, let's say, some arbitrary amount of time is considered as SMDP.
What is the difference between MDP and SMDP?
SMDP has got, I mean, the starting state where the SMDP would start, and then it would evaluate, it would have some internal states, and then it would have some terminating state, and then these terminating states are states of, I mean, the original MDP.
Can I say it is having that time thing? That is the difference?
Yes. Yeah, the time thing. Yeah. After some time delay, we'll go to next stage.
Yes, if I understand correctly, normal MDP doesn't have a time parameter. We assume that transition happens immediately. But in SMDP, we model with a tau as a delay parameter, and in the delay also is accounted for by having a transition states. Am I correct?
Yes.
Okay, ma'am.
Okay, let's proceed to this. So let's first take the same example, the taxi domain example. These are this is green GRBY. Let us take it as a places. These are the obstacles which I am making. So what is the problem? Take this in. Yes. Any doubts? Okay. So the problem is the pick passengers and put passengers. How many places are there? How many places and how many obstacles are there? Yes, come on.
I think seven obstacles.
Madam, that
Sorry,
R,
sorry.
that R is in the corner,
10,
right?
10 obstacles.
R can be anywhere. R can be anywhere.
R can be anywhere, yes. 10 or like how 10?
Destinations are 4.
Obstacles.
Obstacles.
Yeah.
1, 2, 3, 4, 5,
Oh, I'm
6,
sorry.
7, 8.
No, I thought one Y and the above ones are also shaded. Sorry. Yeah. It's
Okay,
8.
okay. 8, I think. Okay. These are not shaded. So 8 obstacles are there. And how many places are there? Four places are there.
Destinations are
4 destinations.
Yes, destinations are there. You're correct. So suppose let us take every move. -1 cost is there. And every passenger, if we like the taxi delivers, it will get +10. And wherever you will drop the place where you drop, there another passenger will come. Basically, we'll have pickup point also there, and then again we'll deliver. This is the process which will be going on. And suppose you try to pick up the passenger. You went to a place to pick up the passenger, but there is no passenger waiting. For that case, -2 cost is there. Or suppose we are dropping off the passenger at the wrong place where the passenger don't want to get down. -5 cost is there. Which means like suppose you're dropping at like from R to B, passenger wants to go, but you're dropping at minus like Y. So I can say that -5 will be the cost there, because passenger don't want to get it down, passenger wants to get it down at B. Is it correct, the whole problem? Yes. Should we proceed?
Yeah.
Okay. So I can write in the just format the problem as what should the taxi do? Go to the place where passenger is. Pick up passenger.
There was a controversy between Apple and Samsung.
Yes. I think equals there. Am I audible?
Yeah.
So pick up passenger. Now go to place where passenger wants to get down, or the destination, I can say. And the next step is drop the passenger. This is the whole thing which we are doing. So let's form it as hierarchical, like the whole format. So let us take, this is the root. So can you tell me like what is the root here? Basically, what do I mean by root? Then we'll proceed forward.
Root means the overall policy, madam.
Anyone else?
Maybe some starting state or something, some initial state.
Basically, the root is the initially what we are going to execute, and actually, it is having the initial task. What is the initial task we are going to do? That is basically the root here. Now coming to the subtask, what are our subtasks? Can I say that pickup as well as the drop are our subtask? What is the main task here? Pickup and drop off. Now, what are the actions here? These are the tasks which you have to do. Now, coming to the actions. To complete the pickup task, what you have to do, you have to navigate where the taxi driver has to go to pick up. To check where it has to go to pick up, the taxi driver has to navigate first. That is the action. And the other action is the taxi driver has to pick up. And if the taxi driver has to drop off also, then also the taxi driver has to navigate and then put down. Am I correct? Yes. Okay. Now the navigation can be north, any direction, east, west, any direction. This is how the whole structure is. Basically, this is called as call graph. Can someone first give me the gist? What is the graph? Like, can someone tell me in detail what I have written, so that I should be sure that everyone has understood and someone can summarize?
Okay, madam. So, yes, the orally we have two tasks: pick up and drop.
Yes.
Pick up a passenger and drop off passenger. And then the subtasks or primitive actions under pickup action is navigate to the place where to be picked up and actually pick up. Those two are the actions under pickup task. Drop off is navigate to the place where we need to be dropped off, and then okay, we call as a put down, drop off the passenger. Okay, and navigation task has four primitive actions, like navigating to north, south, east, west.
Yes. You're correct. Now, can I say this is call graph? As we are calling the subroutines here, it is giving me a clean structure. I have a pickup task. What are the actions here? I have a drop off task. What are the actions here? Can I say that it is giving more clean structure than HAMs? What are HAMs? Can someone give me the gist?
Frankly, I haven't understood HAMs, madam. This is something which is easy to understand.
Okay.
Yeah, maybe. Yeah.
If you haven't understood something, please write in the Slack earlier only so that I can cover the topic again.
No. Only thing is I have to read it twice or thrice, so no problem. But it is more abstract. Hams are more abstract than understanding the call graph.
Okay. Yes, someone else. Last class, I think the other TA has taught about that. What is the full form of HAM, first of all?
Hierarchical abstract machines.
Yes, yes. So, some intuition. What is HAM? Any what do you think? What is HAM?
So I think we are splitting the overall objective into sub tasks, and like basically you have like subroutines, and I think
Yes,
uh,
yes.
it is divided into sub machines, they say.
Yes, yes.
So
If I understand correctly, madam, that those are called finite state machines taking decisions, whereas in call graph only actions.
Yes, yes.
They
So I
yes,
yes,
but,
yes. Carry on. Yes.
so in that context, since decisions are involved, they are more like programming subroutines where you call subroutine within the main routine, and within the subroutine you call another, something like that.
Can I say, if I'm saying that HMs are more confusing, as you told that, as you only told that they are making like having a decision making policies also within that hierarchy. They're
Yes,
having both the hierarchical structure.
yes. There are decision making within that. Yes.
and
So,
they're transferring to another machine. Unlike
yes.
here in this graph, in this example, at least we don't see that.
Yes. So I can say they, if I say that in the easier word, they encapsulate frankly speaking, I have also not seen the video of the lecture of this HM. I jumped to this because I thought that that is covered. I only know the overview of this. So it encapsulates both the hierarchical structure and I can say the decision-making policy within that hierarchy. Because of it, can I say it is more confusing than this call graph, as call graphs are like about understanding the flows and dependencies here.
Yeah, I think fall graphs are like just solve that particular task. Don't think about going to other tasks.
Yes, yes, yes.
So it's like, yeah.
Both are hierarchical.
Yeah, you have to form a hierarchy for both, yeah.
Yes, yes. Okay. So basically, I can say these are more intuitive to understand or to handle. Basically, now coming to this navigate. Okay, this is north, south, east, west. Okay. So basically, navigate here is taking 4 arguments here, as I have said, north, south, east, west. And can I say that it is DAG?
Yes, madam. It must be DAG.
So what is DAG?
DAG is one way, no, it is acyclic graph. So there is no looping back from the leaf action back to the up the hierarchy. There is no reverse on the hierarchy.
Yes, yes. So should I draw these arrows to indicate? Basically, they are acyclic. I can say they are not making any cycle here. Direct acyclic graph. All have direction. That is basically we are saying directed. Acyclic, no cycles or loops are there, and topological ordering is there. Now coming from, if I say from pickup, okay. Suppose from pickup, I'll call navigate. When will I go back to pickup? From route, I'll call pickup. And one more thing, are there actual sequences of actions which are represented here, like in these like boxes? Are they representing like which action to be performed prior to which one else?
Yeah, yes, certainly. Pickup to be performed first before we navigate.
What others think about this? Is there any sequence of actions?
No. No.
Yes.
After pickup, no. When you say sequence of actions as represented in the graph, no order.
Yes.
But actually, in real world, that's what we do. As part of pickup task, we first navigate and then pick up.
So can I say these boxes, order of boxes is not actual sequence of actions?
Yes, that doesn't matter.
Yes. And what does layering imply here?
Layering imply the hierarchy, tasks and primitive actions.
Yes.
Subtasks and primitive actions.
So whenever I'll come to pickup, I can use pickup and navigate here. Similarly, when I come to drop off, I can do navigate and put down here. So basically, they are not read in any order according to my graph.
Yes, no order. Yes.
So taking the original problem, original MDP, let's break into smaller tasks. M0, M1, Mk, where K are the subtasks. This is what we are doing. Each subtask is having some quantities. Let us now go into each of the quantities here. What does this refer to? Yes, come on. What is SI?
So the state.
The states. So what do you think? What are the set of states here?
Pick
This example, the taxi is there. Which
of
yes. You're not audible.
is pick up and drop off state.
Ups and drop off.
Yeah, pick up and drop off.
Are they states?
No, they are actions.
Then what are the states?
States are the places.
Locations.
Yes, places basically. Can I say the location where the taxi is, that is the state?
Yes, so that means all squares, right? Except the cross. That means 1, 2, 3, 4, 5, 25 minus 8.
Okay, yes. So you are saying where can be the taxi can be. So taxi can be anywhere instead of these obstacles. That is what you are saying.
Yes,
So
25 minus 8.
So if I say location of, if I say location of taxis, so how many values it can take? That is 25 minus 8. (25 minus 8 states the taxi can be in. Okay, what is the other state? Location of taxi we discussed. What can be the other state?
Location of passengers.
Yes,
Yeah.
you're right. Location of passenger. So what can be the location of passenger? What values, as we discussed that it can be 25 minus 8 values that location of taxi can be in. Now what are the values the location of passenger can be in? How many values and which are the values?
So
G,
inside
R,
the car and the
G,
four
Y, and Z.
destination.
Earlier I was listening to voice, now I can't listen anyone.
No, madam. The passenger can be in one of the 4 states, RGBY, and taxi.
Yes,
5
correct.
states. 5 states.
Basically, the passenger can be in any of the destination or the places, basic locations, or the taxi, basically. So, where the pickup is valid, like when can the taxi can pick up from these location of the passenger? Can I say when the passenger is in RGBY, then the taxi can pick up? Obviously, if the person is in taxi itself, the passenger is in taxi itself, then obviously there is no point of pickup.
Yes.
Now coming to the third state. What can be the third state? Yes, come
Destination.
on. Destination. So what are the values of the destination?
GRBY.
GBY. So any other value? Okay. Think clear?
Madam, here, how can you calculate total number of states?
Total number of states, basically. Okay. How many states are there? Destination. Okay, destination of passenger, basically. How many locations are there?
Destination locations are 4. Pickup locations also are 4.
Location of passenger. It is not, the state is location of passenger here. The state is not pickup. I was only telling what is the, like, in which locations the pickup can happen. Are you getting my point?
No,
There are
no.
two states. Okay.
No, no. We are thinking of how to enumerate the total number of states. States may include location, but suppose we want to estimate total number of states for this problem.
Okay.
How do we estimate?
Yes, anyone can answer.
One is
Yes, yes.
25 minus 8 is the possible location of the taxi.
Yeah,
is,
and then that is one factor, and then the other things are where is the passenger and what's the destination.
Yes.
so I'm getting confused here how to estimate states. The confusing between actions and
Okay. Actually, the state is not like I have to calculate the overall state. The state is supposed in the form of tuple. The first state is location of taxi. So how many values can be there? 25 minus 8. The other
Yes.
state, this is S1, S2, S3. Every time these three will change. Every time the location of, like, if you'll do something, maybe the location of taxi will remain the same, or it will change, or it will change, or it will change. I can form in the, like, I can have in the form of tuple S1, S2, S3. S1 is suppose location of taxi, which can have 25 minus 8 states. S2 is location of passenger, which can have 5 states. S3 is destination of the passenger, which can have 4 states.
So that means we multiply number of mod of S1 multiplied by mod of S2 multiplied by mod of S3.
No. It's not like that. Okay, let's suppose if you are doing this value iteration only, or like something you're like, okay, value iteration only. What you are doing basically, every state will be modified. Okay. I gave you the example in the very starting. What we do, suppose this example, I have a server. And server is having a battery. And suppose server is having a battery, and these are the devices, device 1, device 2, device 3. Now these devices are communicating with the server. When the server is also communicating with some transmission, they are communicating with some transmission power. And it is doing the computation part and then communicating back. When it is doing the computation and all, or it is communicating, I can say the battery is basically reduced, as well as the time is also reduced. So let us take one state is battery and the other state is time. So battery is independent of time here. In this case, battery is also after one round, after one like simulation, one episode, this battery gets updated and this time gets updated. Similarly, after one episode, the location of taxi get updated, the location of passenger get updated. They are independent of each other. Can I say this? Someone wants to say about this? Am I right if I'm saying this? Yes.
The thing is, I mean, there is similar question asked in assignment that how many states are there, total
Okay.
number of states. So thinking how many such tuples are there, how many possible tuples are there. So we can simply use multiplication and find out how many tuples are there.
Okay.
So a similar question is there in the assignment.
Okay. But if you see,
So if you calculate the tuples, it's multiplying, madam. So
yes, multiplication.
But
If
after
you see-
multiplying, do you have to eliminate some states which are invalid? I don't know.
Correct.
But if you see experimentally, like if you're doing the simulation process, are you multiplying these states? This is my question. As I showed
The all possible combinations could occur.
Okay.
And we might get, I mean, negative rewards. Immediate reward could be negative, even though some state. Karthik sir, I mean, Gopal sir, I think, I mean, even though some states are invalid, we can be in those states, or we may not be in those states, and if we are in those states, we might get some immediate negative rewards. So that can happen.
Okay, so that means let us say 17 is 25 minus 8, 17 multiplied by 4 multiplied by 4. You enumerate all that.
Multiply by 5 and 4.
Yeah. Okay. Yeah. And then invalid states. Okay.
It might include invalid states. It might not occur, but it can be one of the states.
Okay, it can be one of the states. So it's a valid state, right? So that means the total valid states are simply multiplying all three.
You should not say valid. Total number of states are multiplied.
Yeah, total number of states are just multiplying all the three.
Correct. Yes.
Okay, ma'am.
So you are asking about the total combination of states here. Can I say that?
No, do we really call a combination or
those are states? The tuple itself is a state.
There
are three independent parts. Tuple is a state.
Total states.
Correct. Total states. Yes. Total states. Yeah. Yes.
Actually, I was going in the simulation part, like how they are getting updated and all.
Yeah.
So if they are independent, obviously they'll be multiplied, I can say, in that point of view.
Yes, yes.
Let's proceed further. I think we lost the context. Where were we?
We are describing machine. We are describing machine by state action and pseudo
Yes.
reward.
Okay. Can I have M naught as a subtask? Like M naught, these are the M naught, M1 we told. Now, can I have M naught as a subtask as action?
Yes, yes, we can have. We can have. We can have. I
Should
mean,
I
from
consider?
from M0 we can go to M1. From M1 we can go to M2 like that. Yeah. It's like, for M0 we can go to any of the tasks from M1 to MK like that.
Yes.
From M1 we can go up to from M2 to MK.
But what about the reverse?
Reverse is not there because it's a cyclic graph. Yeah.
Because it's DAG, I can say.
Yes.
One way, as the professor told, like we can have the numbered, like suppose AIs are there, the actions are there. AI cannot have, I can say AI cannot consider any MS numbered below AI, so that it shouldn't go reverse. This is the one way of thinking it. First of all, okay, I was explaining the states. Now, what is the actions, first of all? What are the actions? How many primitive actions are there?
The primitive are the 4 navigating actions plus pick up a passenger and drop the passenger.
So can I say 6 6 primitive actions are there?
Yes.
So union of all this MS and okay, the primitive actions. What about the reward here? Okay, what is the pseudo reward? Before what is reward? What is pseudo reward?
I think reward is for the overall MDP, and the pseudo reward is for doing the individual subtasks
Yes.
and whatever you might get there.
Yes. So basically, I can say that rewards associated with the subtask.
Mm-hmm.
Can I say what is the purpose? Let us first what is the purpose of the pseudo rewards? Why its name is pseudo? Let's think intuitively. Why pseudo rewards are in the picture? What do you think?
Madam, because the actual rewards defined are only for primitive actions. Subtasks are the ones we created.
So that if we created, or I can say artificial or pseudo rewards.
Yes.
So what is the main motive of this pseudo reward? What do you think?
To optimize the subtask.
Okay. Can I say that pseudo rewards is we are not waiting for the real distant reward, so that whether we are going in the right lane, we are going in the right path or not, just to indicate that, to guide the agent, like whether the rewards, if we are getting the rewards from the subtask, like just to guide whether we are in the right path or not, by instead of waiting for the distant real reward. Can it be like that? What do you think? Because it's for the subtask only. So can it be, we are not waiting for the real reward. We are just checking whether we are on the right path or not, to guide the agent, to accelerate the learning, basically.
Mm-hmm.
Am I correct by saying this thing? Yes. Okay, let's see. So what are my terminal states? What do you think? What are my terminal states?
In this example, like RGB, are they the terminal state for each subtask?
Okay, suppose I want to go to G, then what is the terminal state?
Yeah, it's G. Once we reach there.
So basically, wherever I want to reach there, so we can have one active states and one terminal states. So can let's denote active states as SI and terminal states as TI. Okay. Now, can I say if I talk about navigate thing? So as long as I am not in RGBY, means navigate has to terminate when I reach one of them, then basically the termination is done. Suppose I have to, if I talk about navigate R, an argument is given to navigate basically. If I talk about navigate R, what do you mean by that? Navigate R, which means that I have to reach R basically. And by reaching R, I'll get the +5. And suppose I read GB by instead of reaching R. So I'll not get any reward, or we can say that some negative reward is there for reaching the wrong state, or -1 is all way, we can say. That is how it works. And one more thing, like about ham and options. Can we say that here we are learning multiple SMDP as we are having, and this is a collective learning solution for SMDP, whereas ham and options are single SMDP. What do you want to comment about this?
No, I haven't understood that statement, madam. So can you just explain? Yeah.
Yes, someone else?
There can be multiple SMDPs even in options or in hams. Depending upon how we can have multiple options, multiple substructures, right?
Okay,
So option corresponds to SMDP.
Yes, options correspond to that.
And there can be multiple options solving main MDP. So there can be multiple SMDPs in options also, in hams also, and here also.
Wait a second. So why this statement is there? Like, is it true that hams and options have single MDP and it learns multiple SMDP? Is it true, or what do you think?
Here it's specifically multiple SMDPs learning. Right?
Yes, here this is specifically multiple SMDP. Now, what about hams and options?
In options, we can have inter-option learning. So there also we can
there.
have, yeah. So there we can have SMDP, then we can have inter-option learning there.
Okay, we can. I think I'll go into it and
In hams, in hams it is not been covered in detail.
I haven't gone in detail about, as I told you also, the previous lectures, because I started with this. If I talk about learning with hams, Basically, I have a constraint set there. Okay, I'll go in detail and then I'll tell you like about the single SMDP or multiple SMDP concept. Okay, let's proceed further.
Okay. Okay.
Wait a second. So talking about SI and TI, TI are the states which it will terminate in, and the rest of the states I can say is SI. Am I correct by saying this? And now if you're in the terminal state and you call an, okay, I'll write it. If you're in terminal state and call an action, I will say call a subtask. What it will do, if I'm in terminal and I'm calling the subtask, what it will do? I'm already in terminal state.
How can, I mean,
Basically, it will return. I'll say
it will,
call.
yeah, that's, yeah.
That is what I was
Yeah.
checking. Now talking about the option thing. If I say an option is there, this is basically how this is working. Now, if I say about the option, how the options work basically, if I start from here, I perform the action, go somewhere else, execute the option. Can I terminate here? As I'm saying here in the call, like all the DAG or everything we learned, we are basically returning if we are in the terminal state. Now, can I come back here in the options? As the earlier one was DAG. What about this? In options, can I return?
Yeah, the thing is, in a state we can start option, in the same state we can also terminate the option.
Okay. I got your
Because
point, but
yeah.
okay.
Because of non-zero beta over there.
So basically, we can return in the same state as you are saying. Is it fine?
In the same state, the option can be started, or in the same, if we reach to that state, the option might be terminated.
Terminated. Yes, you're correct. So basically, I start from here. I'll not end up here. I'll take an action, and in the same state, I can end up here also. We might terminate also, as you said. So is it making sense? So in option, we can land up here. I'll stop. It's fine for me in the option basically. Earlier, what we read that we are not making like as it is DAG, so we can't end up here. Is it clear both the things? Okay. So how do value functions work? The collection of SMDPs, we'll say. So let's take one MI. So as we did, we have SI, AI, and RI. These are the states. We have actions and we have rewards here. And then the distribution and all we'll have. And if I say about the reward basically, if you drop off, you'll have the like you are at your goal, as we saw in the taxi thing. If you're dropping off, you are getting the reward here. If you're wrong picking up, like if the passenger is not there and you are picking up, then you are getting a negative reward. Or if you are dropping it off at the wrong place, then you are also getting the negative reward. That is what we saw. Okay. Now coming to this part, tau. Let us say tau is the number of steps going to take. Sorry. We'll write and then we'll go through everything. Can someone explain me what I have written first of all? Yes, come on.
These are
Yes.
transition probabilities for
Yes.
machine MA or for
Yes. Yes. For
which
AH
is
subtask, I can say.
SMDP. Yeah.
For AH subtask, I can say that is why I'm using machine MA.
Yes.
And tau is the number of steps it is
Yes.
going to take. I can say to get into S bar, which is okay. Sorry, written this S bar, which is the final state. Is it clear? So by how many time steps the subtask, which is corresponding to A, it will take to complete, which is determined by MA. Ath subtask, ath machine here I'm taking, that is what is here. Now coming to the reward part. Now can someone explain what is this reward? Yes, someone was explaining before that one is pseudo reward, one is reward. Now I'm talking about the RI only, not the pseudo reward. Someone told earlier also what is the reward here. Yes, when they were you were telling about the difference between the reward and pseudo reward. So what is the reward now? Come on.
Yeah. Is it for like the whole MDP?
Yes, yes. Can I say the summation of the rewards? Tell right. Can I say it's the summation of the rewards
Mm-hmm.
that you are going to take? Or, oh, sorry, that you're going to get, I'll say. While action is equal to A, are being executed. That is what the summation of the rewards, as you only told that this is the difference between this pseudo reward and the normal reward, which is pseudo reward is associated with the subtask only, and the whole reward we are talking about the whole reward here. So basically, we are executing the policy at every step. We are going to get the reward. I'll write here in more detail. What we are doing, execute the policy basically. Every step we are executing the policy. Getting some rewards. and then just accumulating it. That is the total reward, what we are saying. Is it clear?
Madam, that is for the normal MDP, normal
Yes,
thing.
yes.
In case of this SMDP, in case of SMDP, the actual reward is nothing but summation of pseudo rewards. Oh, can I say?
What others think about this?
No, for example, that Ri, you said Ri of S comma A, S dash comma tau. That is the actual reward, right? For the end of the subtask A, correct? And so if tau is equal to 0, this is same as yeah, I don't know. I'm trying to visualize, but somewhere I lost the thread.
What others want to say about this? Basically, we can't say that it is the sum of the pseudo rewards. Why? Yes, can someone tell? What others think? Yes, come on. Second last day today, so let's have this session interactive one.
So this is I think, yeah. Karthik, go ahead. Karthik.
Yeah, I thought like pseudo reward is for the subtask, and so that should not come here.
Yes.
Like it won't be like pseudo reward might be for optimizing the subtask as well. So that should not ideally come here. That should be like a stepping factor there.
Oh, maybe so. Pseudo reward is a guiding one for the primitive reward. I don't.
Can someone tell me whether I'm writing correct or not? Maybe I can also be wrong. What I have written. Yes, come on. Can you see my screen first?
Yeah.
What's written there? R total T.
Our environment T. Basically, at time T, I'm getting a reward. Or I can say reward at time T is equal to reward. What I'm trying to say is this is the actual reward received from the environment at time T plus the pseudo reward at time T. This is basically if we talk about the hierarchical RL or have the shape of the pseudo reward, include the pseudo reward in the picture. Is it like that? Actual rewards which we are receiving and the pseudo reward at time T?
Not sure. I'm not sure.
Is completion reward for task plus pseudo reward?
Completion reward plus pseudo rewards. You are absolutely correct. That is what I am referring to as actual reward which are received from the environment. Total rewards, basically. The completion rewards. Okay, let's proceed further and see. Till this time, I was only let's ignore the pseudo rewards for the time. Till this part, I'm only saying that it is a summation of the rewards, or I can say here, if we are doing the sampling thing, I can say that basically I'm doing the sampling, so reward expectation. Let's ignore this S bar tau everything. Write it as simply like this, basically. As I told that this is expectation. If you want to include the pseudo rewards, then this will be added. We are not taking into consideration to make it simpler. Now, can someone tell me what is this? Yes, come on. Come on, let's try at least.
Is this SMDP reward?
Yes.
Is this SMDP reward?
So what we are doing basically, we are conditioning on S, A, pi, like this is the expected reward, okay, this is the discount factor, okay. What is there anything which is changed or something tricky here?
For me, this looks like a value function.
This is gamma raised to tau. Gamma raised to tau minus 1 RT plus tau. Will it run infinitely over here? Plus what? Professor has written, I mean, dot dot dot. So is this SMDP reward?
Is it SMDP or MDP?
SMDP reward.
SMDP. What is the difference? What is this pi here?
It's by the policy that is followed in SMDP.
So why we are taking the policy here? Will it be tricky if I am saying that pi is already known to me, policy is already, why policy should be already known to me, first thing?
Yeah, so
okay,
SMDP
state is known, action is known, what are the expected reward, it is fine. Now why this policy comes into picture? And
so every machine has got fixed policy, so that is the policy of that machine.
Yes. So is it somewhat complicated, or is it policy given is okay? Why we need the policy?
But without policy, we cannot compute that RT plus 1, RT plus 2, right? So it's expectation over pi, actually. Expectation.
Yes. Someone else want to comment on this?
So will it terminate with tau? This summation will it terminate? Gamma raised to t minus 1 RT plus tau, will it terminate over there?
What? I didn't got your point.
This expectation is summation RT plus gamma RT plus 1 plus gamma square RT plus 2.
Yes.
Will it terminate or will it run infinitely?
Okay. Why we use discounted rewards?
Because we have this is SMDP, and SMDP, one of the properties tau. So tau is the random value it can take, right?
Yes,
the SMDP runs. So which is infinite also, which can be infinite.
But can I say by discounted rewards that infinity part is gone?
It's taken care of, no doubt.
Because the last terms, like the most, the history is like negligible there.
Yeah.
Now, one more thing. So now what I have called A here. Now in in this part, hierarchical part, now A is calling A dash, I can say, and A dash might call A double dash. Can I say? Suppose I have root, I might call pickup here when the action root is called, so that to know about that, the reward, then pickup might call what is this? Navigate and navigate basically. Pickup might call navigate here, and navigate might call south here. Can these things can happen?
Yes.
So do I need the policy because of this reason?
Yeah. So if we are in pickup, we require some policy. If we are in navigate, we require some policy.
Yes. Are you getting the intuition behind whole thing, or Basically, I need to know what was the entire policy that was executed to compute this expectation. So that is why I am conditioning on this pi thing. Should I proceed? Okay, let's proceed. Now let us write down the value function here. I'll come down. What is it? Can someone explain me this in detail, basically? What is this? V pi is the value function. I can say of the state S in the task I. Is it correct? I'm having the task I in the state S. What is the value function? That is what I'm computing. So what I'm doing is I will say I'll first pick up the cost or reward corresponding to the first action. That is R pi of R pi IS. Is it correct? Here I'm assuming that, as you also told now only, that pi is deterministic here. That is why this summation of pi is missing, I can say.
Summation or actions.
Summation of our actions, because the pi is deterministic.
Yeah.
So is this value function, can you explain the whole thing?
The first part is like immediate reward. It's a Bellman equation, like immediate reward
Yes.
plus, I mean, this backup from, it's a full backup from.
Yes,
I mean,
yes, yes. That is what we have done earlier many times, and this is how we are doing here.
Yeah.
So now coming to projected value function. What do you mean by, is this a projected value function first thing, and what do you mean by projected value function? Yes, come on. Can I say that I am only worried about this task I, finishing of this task I. I'm not worried about what happens after task I. Basically, projected value function, I can say which, this is a value function only for this task, until this task I only. So can I say this is the Bellman equation of the projected value function? Yes, come on.
Yes, it's a Bellman equation.
As I'm only worried about this task I don't care about what happens after it.
Yes, yes.
So here we are talking about this projected value function.
It's normal MDP also, it's a projected value function, right? Normal MDP also.
Can you repeat? I didn't got your
In normal MDP also, it is projected
Yes.
value function, right? Only I is not, different machines are not there.
Yes. In
So,
that case, can I say because different machines are not there, that is why it's a projected value function?
I mean, it's been calculated from immediate reward and full backup. That's why it's a projected value function, right?
But okay, yes,
Why
because
the word projected is
yeah.
there?
Uh-huh.
It is calculated from backup, right? And then immediate reward. That's a projected value function.
Yes, sir. The word projected doesn't seem to have a special meaning here.
Yes, yeah.
Can I say, if I talk about this value function, why we don't take the actual true value function? Why we take this projected value function? Like a question arise. Why simple? Like we can think about function
Maybe
approximate.
what professor told. No, every time we are taking projected value function, here this I got added because it's a ith machine. That's it. Nothing, no other difference.
Can I say that because this like we are focusing on one task or so, because the state space is large or continuous in FTP as well. So that is why we are not taking the true value function, or I can say it's a function approximator in this case. Just projected value function can be termed as like approximation for estimated the value functions.
Context.
Because
Yeah. Yeah.
let's switch back to what we were doing. So if I talk about our pi of s, we are accumulating over like the rewards here. So project like it is a total reward I'm accumulating till the end. Basically, that is there. That is clear. Basically, now coming to what is left in this equation. I'll write this again. Wait a second. Let's keep it as this one. Now, can someone explain me what is the change which I am doing? What is this V pi is? Can I say it is the accumulated reward, or how can I say this?
Yeah. So this is a reward of action. Like if it is action which selects a machine, by IS selects the action that might select
Yes.
a machine, and it is
So
that.
can I say it is the projected value function of pi I of s? It is the actually
Action.
the
Correct.
reward that I have accumulated till end of that.
Correct. Yeah.
Now coming to the other equation, write more clearly. I think I'm making mess here. Now, what is this? What is first q pi? Like, what is whole thing? First of all, what is this? Value of, I can say, state S and subtask A.
Yes. Yes.
That is immediate reward
Hmm.
of the subtask.
Okay. Now, can I say it as completion function, and how can I say this as like, is it fine if I say this is a completion function? Are we completing it here? Like, is this a completion function? Can I say it is the total cost, or it is the cost or the reward, like you're going to accumulate in the subtask I, basically? The cost you are going to accumulate in subtask I after the action A is done, and starting from S, this whole. I'll write the equations and then we'll go again. Wait a second. We'll go again. I'll just write this. I'll compute it. Can someone give me the whole gist what I have written? Yes. Now, what is happening is, basically, I have completed action A first thing in some state S bar. Then what I'm looking is that how much reward I'm accumulating from S bar to the end of the state. That is what I'm saying completion function. What exactly is? Once I'm completing this action A, I'm accumulating the reward. Are you getting? Basically, how much more reward I will get after the completion of subtask I. Can I say this as completion function?
Madam, one general question. Why this introduced a new completion function, which actually can be valid even for regular MDPs as well, right? This
What other think about this? Like, can completion function be valid for the MDPs? Yes, come on.
Yes, I wanted to understand the motivation behind CPI.
Now here, I mean, this Qmax, no, it's value function decomposition. The thing is, I mean, this V pi AS could be decomposed further, and so on. Like, we can have depth, and we can take completion function from each one
Yes.
till we hit a primitive action. That's why CPI is used over here.
So can we say that completion function is not in MDP as we are not
Right,
decomposing?
right, because this VPI AS is an immediate reward. Right, it's a the thing
That
is
is okay.
always a primitive action in case of MDP.
Yes, that is okay. Yes.
Yeah. So we need such decomposition is not required in case of normal MDP.
What about completion function? Can you give the gist? What is completion function? What do you think? What is it?
So I'm calling, let's say, if I take action A, which happens to be calling a subtask, whatever the reward written by that subtask or projected value function from that subtask, plus I mean whatever projected, whatever I mean this backup from the next state after I mean time after time tau. It's like that full backup
Can I
after time
say
tau. Yeah.
after this task, how much reward you will get? That is the completion function.
Correct. Yeah. But the
So
task might not terminate in S prime, right? Or task
yes.
will terminate, yeah, in S prime.
Basically, if I'm saying that this is the subtask I, so how much more reward you will get? That is the termination function. Oh, sorry, completion function. Is it
Yeah.
correct by saying that?
Mm-hmm. Will the task terminate in S prime? Will the SMDP
No.
terminate?
S prime. It's not. We are saying that after S prime, how much reward is accumulating? That is completion function.
Yeah. So the thing is, SMDP will run. It will call a subtask, right?
Yes.
So whatever reward that is earned by, I mean, calling subtask is the first term.
Yes.
And then
Yes.
after returning from
Yes.
subtask, it will complete the SMDP after time period tau.
Yes.
And
Yes.
then whatever the value function that we get is the second part. Is it like that?
Yes. Yes. Absolutely correct.
Mm-hmm.
So everyone got the thing. Everyone got this point. Okay, now can you explain this point, this composite primitive, what I have written?
Yeah, so the first part is whatever Q value function or action value function of this task A, if it is composite, if it is primitive action, whatever our normal backup rate.
So if it is composite,
If it is composite, it is calling a subtask and whatever value
it's
function written
like
by
one of
that
the
composite
subtask.
function.
Yes.
Yeah, yeah. So we can further decompose, right?
Yes. Can I say if it is primitive action, it is the, we are saying that this is the expected value of the reward.
Correct.
And
Yeah.
if it is composite, it is just like one of the subtasks.
Yes. Yeah. Yes.
Let's proceed.
This value decomposition, I mean, from root, it is very interesting. V50S is very interesting. So that is the main crux of it.
Actually, topic lot of music as well. Now, if I say that I want to compute this Q, can I say I need the C for computing? And the V, if it is composite action, I will go down and ask for this Q. And if it is primitive, it will return me. That is what it is doing. So, can I say it is some kind of hierarchical thing? Recursively going down, getting up.
Yes, yes, yes.
Now, coming to this policy, let us say the policies which I am going to follow for each of the K subtasks, like for M0 to Mk. Pi naught, let us take it for M0, pi1 for M1, and so on. So let us write the value functions as you were saying. Let us make it more interesting. So suppose I'm in zeroth subtask, value function of zeroth subtask in the state S basically. Can I write it like this?
Yes, yes.
So now can I say that phi naught will call some other action below it, and the action will call some other action?
Yes, yes. Yeah.
Can you explain how, like, what will happen, what I'm saying?
Yeah. So it is, first thing is, it will, let's say, call A1 action. Phi naught S calls A1 action, which
Okay,
happens to be subtask.
okay, phi naught S calls A1 action.
And A1 is, let's say, subtask. So
Hmm.
what can be written is, this can be written as this V pi 0 comma S can be written as completion function first, and then V pi A1S.
Is it like this?
Yes, yes, yeah. And then
A1.
V pi A1S might call A2S.
Yes,
So
that is
that
what
is
is
C.
happening.
Yeah, that is what
So
is happening. Yeah.
V pi, I can say A2S plus C pi. I'll write whole basically. Here
Yeah.
also I'll write the whole.
Till
C pi.
till 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 we hit a primitive action, and then we return. Yeah.
So if I first act like if A2 is basically here all, so A1 is A2. Is it correct by saying this? So basically, what is happening is phi naught S is basically A1 here.
Yes, yes.
So now I'm going to now it is calling A2. That is how it is proceeding. The first action, like
Yeah.
phi naught will call some other action below its first action. It will call some other below it, right? That is what is
So this is,
happening.
the first one is completion function of zero, or
Hmm.
the zeroth machine. Second one is completion function of first machine, and
So
so
can
on.
I
Yeah.
write the whole equation as it is, right? C pi 0 S A1 plus C pi A1
A1,
A2.
A1S. Correct.
So can I write this?
Yes, yes. Yeah.
So I will look at completion function for that action. Then I will go down and look at the completion function for the choice I made in the subtask. And if I reach the end, I'll write this V pi, right?
Yeah. Yes.
That is what is happening. So here I can just use this completion function also. So can I say the root task, what we have we are having some completion cost or completion function. After you finish A1, okay, I'll write it. If I am going to some sub level, I do not care what is happening in A1. Is it so, or we have to care what is happening in A1, the above action? Yes, come on.
You mean to say for reward?
Yes.
We need not care about the pseudo rewards, right?
Yes, yes. If I say that, okay,
So
like how,
value function of sub level is considered in determining value function of upper level, right?
Yes, that is what value
So
function of
do we need
sub-level.
to care?
Actually, it is difficult for us to maintain the bookkeeping as well.
That part, I mean, somehow it's hurriedly been told. And we have to read paper. In the class also, it's hurriedly told.
Yes, I'm getting. It's suppose I'm thinking how to go through it. I'm executing subtask 1. Let's go it slowly. And task end. After that, whatever will happen till 100, if I have to, obviously I have to, if I'll go through this, I have to maintain that, because we are saying this value function, we have to maintain. If we are going through this like till 100, we have to remember that one. Is it feasible? Whatever happened till 100, all that information has to brought back basically to subtask 1. Is it difficult or is it okay?
So it's difficult.
It's quite difficult. So that is why basically an efficient bookkeeping should be there, or something, some options or something should be brought up, because it is very difficult for us to maintain that bookkeeping thing. After this thing, the professor has switched to the other the other lecture, or anything was taught here also. I actually don't know.
It is option discovery. Third lecture option discovery.
Option discovery. So can I say this is the drawback for this? What is the solution? Is there a solution given?
He has given solution, yeah. For hierarchically optimal, he has given solution. For
What is the
multiple bookkeeping and like that, yeah, as you were saying.
Okay. So
For
what is the
hierarchy.
solution given?
So that is not very well understood. It is in last 1 or 2 minutes he has given. Last 2 minutes to.
Yeah, he talked about max Q0, max QQ concepts.
That's something.
Max QQ is when, I mean, we consider pseudo reward.
Yeah.
Yes.
Max Q hyphen Q and max Q hyphen 0.
So can someone tell me what is the gist? I also don't. I'm unable to recall it.
When you consider pseudo reward, we have max Q hyphen Q. Double Q is there. Max Q hyphen Q. Max QQ. Yeah.
It's like this.
Yeah, correct. Yeah.
Okay.
And max Q0.
Okay. So what is the difference
And
between
then,
max?
so we consider, I mean, pseudo reward in max QQ. We have to consider pseudo reward and rework on decomposition by using multiple Qs.
Yes.
Yeah, so that's what
So,
he said.
so
And you
how
read it.
pseudo
Read from the
rewards
paper.
that I also listen.
Yeah.
So how the pseudo rewards are helping? Okay, or either I'll take this in next class. We'll go in just an overview. What is this max QQ and max Q0? I'll cover that.
Okay.
I think what I. Okay, I'll cover this thing.
This max Q is recursively optimal. To convert to hierarchical optimal, I mean,
Okay.
something is to be done.
I also think this is something recursively they are decomposing the Q value of something. Okay. Some Q learning is there, methods like Q learning is here in this method basically in hierarchical fashion. Okay, so we'll learn this I'll give you the gist what is basically behind this max Q1, max Q0. So let's proceed further. Till now, the intuition behind this, is it clear? And what are the next, as the time is running, so what are the next topics which you want, like they should be covered in the last lecture, because now only the last lecture is left after this. What are the main topics? What are like revision thing, like how should I do?
Gopal sir, please go ahead. I will tell the list.
I think when I get a hope of moved one step further, I am falling back 2 steps back. So yeah, so what I feel good, madam, next class, if we can review all the concepts at connecting each concept, each model. For example, I know hierarchical learning is to reduce state space, and in that state space, we talked about 3 models and how each of these 3 models are different. Like that, at a high level, you can give overview of all the topics of reinforcement learning, so that at least we can even if I haven't gone through the algorithms in depth, understood, but at least at a conceptual level, we can say that in elementary level 0 understanding is something we feel confident about it before I venture into further into reading those algorithms. That is one thing. And another observation I find is that the entire discussion of the RL course, Bellman equation is the central one, right? And all algorithms are interpreting and basically converting that value function or Q function into a iteration model, and basically is revolving around the Bellman's equation. Okay. Maybe you can explain that how this Bellman's equation is interpreted in different algorithms. Okay. Anyway, starting from scratch, the whole thing. Okay. Maybe and at least I feel that I can. Yeah. So actually, it is my problem because I lost somewhere. I'm trying hard to make sense of it, but somewhere yeah, we lost some threads or some links connecting. So if you fill up that links, then we can get aha moment, and in 1 week we can get reasonably confident of at least 60-70% to face the exam. Yeah.
Okay. So what I'll do is I'll write all the topics in the form of presentation or points basically in the page, and then explain each and every one how they are connected to each other, what are the drawbacks that we came to the other topic, and whole intuition behind each of the topic.
Exactly. Great. That is one.
Anyone else want to give the feedback related this? Okay, let's go to option discovery. Actually, I thought that I'll teach this form DP, but this was left, so I started with this. Actually, I like that topic personally so much.
So the sir has mentioned about discovery as something like that it's an ongoing research topic. But the sad part of it is he starts covering it, loading up our brains. So actually, yeah, it's actually someone asked the question. I think, how do you discover options? Right? That's an interesting question.
Yes.
It's an interesting question. Okay, we only learned how to use options, how to model options, but we never. We don't know actually how to find options in a given problem. Okay.
Yes.
But,
so now, can someone tell me what is this options? When do you call an what are the uses? What are the benefits? like reusability. I can say cut down on exploration, transfer. Like, can you tell me?
Yeah, if you take an analogy of software programming, like how various functions and subroutines help reduce the effort. For example, if we don't have options, probably we need a huge state space, state space. And basically by discovering those options, we are reducing the resources required for basically we no, in a way, actually what we are doing is that instead of one gigantic policy, we are converting that into a set of options uh, uh, via options or via abstract machines. And so, but the issue is, for example, in programming, how do you discover what are the various subroutines to be written actually? We identify what is the reuse, how many times that particular policy or sub policy is being used, and how many times. And it comes from knowledge, right? It comes from the domain of the game or domain of the problem. Yeah, so I don't know. I know it is a tricky, but is there any algorithm? I don't think there is an algorithm, right, for discovering option discovery, for option discovery. It is
What
a
are, okay. So what are bottlenecks basically? I'll come. Can I
okay.
say that to find an option, this is used, as you are saying, is there any algorithm to find an option, like we are using this bottleneck?
Okay, I don't know. Maybe you can explain what is bottleneck. So,
Yes. Someone want to comment about this? What is bottleneck? What by the name? What do you think? What is bottleneck?
The constricting states, the deciding, like some things that has to be done, but yeah, it's constricting.
Yes. Can I say, like, there are a lot of things like has to pass through it, but from reaching to one point to another, but there is a narrow like this constriction there, or that is why,
Mhm.
or
Yeah.
what is bottleneck state? What do you think? If you're talking in this context, what is bottleneck state? Or if you are talking about this door example which sir gave, what is this, like, what is bottleneck state? Can I say bottleneck state is the state in the environment that is frequently visited when we are transitioning from one subtask to another? Here, basically, from moving from one to a door to another, the door, these doorway states can be considered as the bottleneck states.
Mm-hmm.
Is it correct by saying that?
Yeah.
What are the other things? What do you think that about this doorway example? What do you want to say?
most frequently acted upon, most frequent action.
Yes.
Most frequent action. For example, if you consider several multiple episodes,
Yes.
what is the state action? No, I don't know. Whether you say it is, what is the most frequent state action pair?
Yes. Yes.
What is
So
the most?
basically, yes. Yes. Come on. Carry on.
Yeah, what is the most thread? The state action pair sequence that gets repeated in several episodes.
Hmm. Yes, that is what we can say is. I can say that states which are frequently visited, that is what we can say there as a bottleneck here.
Not only states, actions. State action pairs, that's what I feel. Anyway, we visit multiple times, but state action pair is the one we are interested in.
Can I say that here in the doorway also, like from one half of the MDP to going to go to the other half of the MDP, the doorways are actually the bottlenecks because they are allowing the access. How do you find these bottlenecks? You were telling. Okay, let's dig deep. I think several example like approaches are given. What do you mean by this diverse density approach? Let's see in detail. First of all, before going, let us say we have two types of trajectories. One is successful trajectory. Another is unsuccessful trajectory. What do you mean by these two trajectories?
Yes, successful trajectory is the one which ends up in the goal state.
Where agent is achieved its goal in MDP. Okay. Where agent failed to achieve the goal, can I say that is unsuccessful trajectory?
Yes.
Now, coming to the next step in diverse dense, we analyze the state frequency, as you said. Agent checks which states appear more frequently in the successful trajectory. Can I say?
Yes.
Basically, agent is checking which states are appearing frequently, and it is also checking that the states that appear in unsuccessful trajectory as well. Now, the states, I can say, that appears more commonly in successful and uncommonly in or rarely in unsuccessful. Can I say these states as bottleneck? Yes. What are they trying to say is, if most of the times you succeed in passing through that particular state, and most of the failures are not there involving that state is probably essential for the success.
Or maybe, madam, or we can rephrase like this: for towards reaching the goal state.
Yes.
Is the state through which most of the episodes pass through.
Okay. Yes. Most of the episodes. Okay. In the other way, what others want to say about this?
See, let us say there are 100 episodes towards the goal state. Out of that, 70 episodes are successful. And all these 100 pass through S. So 70 of them successful. So that state, yes, is the bottleneck because that is required for success. And that's also the reason for unsuccessful.
What others want to say about this? Yes, come on.
Because there is no other state.
I'm
be-
getting the point. Yes.
Yeah.
What about others?
Yeah, I agree. That is it states that would be the key state and without which we cannot succeed. So that's the indication.
Yes.
And it might be difficult to achieve
So what is the other approach given by the professor? I think, yes. Come on. Betweenness, I think. How many approaches are discussed in the class? Diverse density approach. Something called betweenness. Yes, come on. Graph partitioning or am I audible?
Yes, madam. So I have understood whatever I understood. I can recall. Maybe I don't know whether betweenness I have heard this term or not. So
What about others? Was this the term given? Am I missing something or?
yeah. So maybe he shared it. Maybe we could not get it. I have to refer my notes.
Yeah. So between this, I think he had given.
Betweenness, yes. Basically, betweenness. What do you think? What is betweenness? It is. Someone wants to discuss about it.
Yes. Betweenness. Yeah, yes, madam. It is there in my notes. I just read out. It has not gotten into my head. A node has a high betweenness if a node finds a lot of shortest paths between.
So can I say that the measure of wait a second. The number of shortest path that pass through a particular node or particular vertex the measure of that is called as betweenness. How many number of shortest paths are basically going through that vertices?
Yes.
And nodes with the higher betweenness centrality, if I say, often act as bottleneck since there are large number of shortest path there. So in one way, if the node is having the high betweenness centrality, we are saying it is acting as a bottleneck. If this is basically removed, I can say if these nodes were removed, it will become like the overall flow or connectivity of the network is distorted. So that is what it is, the concept of network analysis. Shortest path basically between the pair of the vertices. That is what is discussed here. What is the other technique? Betweenness. The other one was this bottleneck.
Graph partitioning. That is one method mentioned by sir.
What is the other technique? Graph Okay. Graph partitioning.
Graph partitioning, diversity, density, and betweenness. 3 things.
And I think some small world properties or something.
Yes, small world options to cut down exploration time. The best use of data.
So do you got this bottleneck? Do you got this? Diverse density approach and betweenness?
Yes. Intuitively, yes.
So basically, graph partitioning is, I think, to find the options.
Yes, maybe. Yes.
And
So he's
talking about the small world phenomena. What are your views? What are small world phenomena or small world options? What do you think? What is, first of all, small world network? Okay, that is out of scope, but still, if they are using the word small world, it comes from small world network. Actually, not relating to this, like small world network, it is a graph only where most of the nodes, they are not the neighbors.
Yeah, it says number of random trajectories can define options.
Basically, most of the nodes, if I talk about the small world network, most of the nodes, they are not the neighbors. But most of the nodes, they can be reached from like every other node by small step. Like we can reach from one node to the another node by the small steps or the small hops. Yeah, I think professor has also mentioned about the social networks thing. This is the social network only, like we can reach the other node through the small hops. That is why it is written small world. We can reach from one state to another. That is the main idea behind this small world phenomena.
Yes. The similar concept in social network analysis is called 7 degrees of freedom. You can reach any person in the world by connecting maximum of 7 people in between.
Okay. So this is these are the techniques basically for this. Any doubts? This was, I think, just a short lecture in which some of the terms were discussed about how this water and everything is done, the techniques and all. Do you want form DP to be discussed now or tomorrow only?
Yeah, not. I think that is relatively easy to comprehend, madam. I just gone through, just sketchily gone through it, but there's relatively easy to understand compared to this higher.
HMM is not discussed in the class, is it? Hidden Markov model?
No, POM DP is discussed. Solving POM DP. Markov models, no.
Hidden Markov model. Okay.
No. Only POM DP. Only POM DP. It's a looks like it's a very short one. Week one is purely about POM DP and a small problem of how to solve POM DP.
Okay. So tomorrow we'll discuss that. So next lecture, I'll come up with the revision session. Any doubts? Okay then. Thank you, class.
Thank you, madam.
Thank you.